Hi everyone, welcome back to the Sagar TechGate channel. So in this video, we'll explore a gate level modeling with some suitable example. Already I gave some introduction about gate level modeling and how delays are associated with the different gates. So how to specify the delays while instantiating the uh, gates. How to use the primitives to build a digital circuits using a gate level modeling. Actually, this is the lowest level of abstraction levels in Verilog. We never prefer to build a complex circuits by using this gate level modeling, but at basic level you need to understand how digital circuits are designed using gates. So in this video I'll give some examples how to write a Verilog codes of a different simple digital circuits. Let's begin with off adder. Now having two inputs a comma b and the output sum and carry. This is off adder. You know how to design off adder. So by using a simple truth table, the sum is like XOR of this inputs, and whereas this output, the carry is a AND gate of this inputs. So how do I represent this off adder in terms of internal gates? Now this is a simple gate level diagram for this off adder. So now XOR and AND gates, two inputs a comma b and sum and carry. How do I write a Verilog code, especially in a gate level modeling? So we have two gates here, XOR and AND gate. So we initiate these two primitives in our module, okay, and you connect properly to get a proper output. Now, so if you see in Verilog, everything is a module. So now I declare one module. The module name is off adder, having the ports A, B, sum and carry, and I declare these ports A, B as the input and sum carry as the outputs. So how do I write a Verilog code in gate level modeling for this off adder? So if we see this circuit diagram having a two gates, XOR and AND gates. Now I'll instantiate this XOR gate. This is instant name. So now one output, the sum, the XOR output is the sum. Now here is a sum, and the remaining or the input signal, the AB as the input for this XOR gate. Same way, I can instantiate this AND gate to get the carry outputs. So AND gate, the instant name is Z2, then the output is a carry. Now this having two inputs A comma B. This is the simplest way to write a Verilog code for these circuits in terms of gate. Now if you observe, so this Verilog contains the two gates. Just by using that wire we connect all these gates. So now you may get a doubt. So now we didn't specify the data types. So if I didn't specify any data type, then default this AB sum carry is the wire type only. So we have a two data type, reg and wire. If I didn't specify any data type with respect to that signal, then it default is the wire type only. And also I didn't specify the size also. So these are all 1-bit signals. Clear? And wire type. So now see another example. We have a full adder having a three inputs A, comma B, comma C in, and the two outputs sum and carry. Three inputs A, B and C in, and the two outputs sum and carry. Now if you see this expression for sum, A XOR B XOR C in, so carry is equal AB plus BCN plus ACN. So many ways we can design. So there's a simple circuit diagram. I'm not giving much time. I'm not taking much time. Okay. So now just I'll draw the gate level diagram for this full adder. So if you have a diagram with a gate level diagram especially, then you can write Verilog code by seeing that circuit, right? Now see, this is a module, full adder gate having inputs A, B, C in, sum and carry. I am declaring these A, B, C in as an input, sum carry as the outputs. So already we discussed this wire concept. So if you want to interconnect these gates inside this module, okay, then you'll use a signal W1, W2, W3 as a wire types. So we should declare these signals prior to use. So those are the wire types. So now one output of this gate is connected to the input of another gate. So now we need this intermediate signal known as a wire type. Okay. So I'll declare three wire signals, wire 1, wire 2 and wire 3. So now XOR. So this is a XOR. The output is W1. For this XOR, what is the output? W1. So first signal is the output. The remaining signals are the inputs. Now AB as the inputs. Now we are getting the output of this XOR as a W1, known as a W1. So another XOR we have. So now this XOR contains two input. One input is coming from the output of this first XOR. So what is that signal we call W1? So W1 is the input for this XOR, and another input for this XOR is the C in. So now it has the two inputs W1 and C in. Okay, so now XOR W1 and Cin as a input. Now sum as a output. Now for this XOR gate, this XOR sum as a output having two inputs W1 and Cin. Same way we have another two AND gates here. Now here this AND gates. So the what is the output of the AND gate? W2. So and W2 is the output having two inputs. One is B input, another is the A input. It has a two input A comma B and one output W2. Same way this AND gate we instantiate. So AND gate. So W3 is output. The input for this AND gate, one input is W1. One input is W1 coming from the output of the first XOR gate. Another input is the Cin, directly we can give. So for this AND gate, so W3 is output, W1 and Cin is the input. Now we'll use OR gate. So has two input W2 and W3 as the input coming from the output of these two AND gates. Now carry is the output. So we instantiate the gate OR. So carry as the output and these two are input signal W2 and W3. So by seeing this circuit, okay, in terms of gates, so we can write Verilog code directly. You should know how to connect these gates, okay? So which output of the gate is connected to the input of another gate. If you know that, then directly we can write a Verilog code. So see another example. So 1-bit full adder using off adder. So this is also known as a structural level modeling, okay? By instantiating another model in the given model, okay? We can, so for example, if you want to design a full adder, we require two off adders. So how do I instantiate these two off adders in my full adder model? This is structural level of doing, right? Now this, off adder code, simply just now we discussed, right? So now I write a code in data flow modeling, okay? So just now we discussed in gate level modeling, there's simple off adder circuits. Now here, assign some A, X or B, okay? Assign carry A and B. There's a simple writing a code in data flow modeling. Our aim is to design a full adder using a two off adders. So this is structural modeling. So now how do I design this full adder? Now I have a two off adders and one OR gate. Like that I connect, then I'll get a full adder. So now I instantiate this off adder 1 and off adder 2 and OR gate in a given full adder model. So just I'll write a model full adder having a three input A, B and C and the output sum and carry. I declare. So now I specify the direction inside this parenthesis. This is a best practice. Okay. So now we can specify directions and data type here itself. Clear? So model name full adder, the input A comma B C and output sum carry. So now I'll use the intermediate signals to connect different entities in the circuit. Okay, W1, W2, W3. These are my wide signals. Now first off adder. So what is the off adder? So now you know that already this is the off adder. Clear? So now instantiate this off adder. So the model name is the off adder. Off adder instant name is HA1. So what are the input? A comma B as the input and sum is output. The W1 is the output. Okay. W2 is the another output. Now W1 represents the sum actually and W2 represents the carry for this off adder. Now we have two outputs W1 and W2. Same way another off adder I instantiate here. So the input for this off adder is one is W1, another is the C. Now see off adder 2. One input is C. Another input for this off adder is a W1. So another input is a W1. So sum and carry. Clear? So the output is sum and another output is the carry. So now while instantiating, you should follow the same order. Already we discussed, okay, how many ways we can instantiate, how we are connecting the ports, okay, while instantiating. Clear? Port by name, port by order, already we discussed. If not, please visit that video, you'll get an idea. So how we are instantiating the model, one model in another model, how we are connecting the ports. Clear? So now these are the inputs, these are sum and carry. These are the inputs, sum and carry. Same way, in the same order, I need to provide. C is the one input, W1 is another input. The output is sum and the W3 is the carry. Now to get complete carry, okay, what are this is the OR gate I instantiate, okay, assign carry equal to W2 and W3 is the input. Okay, I will use the data flow modeling here. This my intention is not here. I'm describing the circuit in terms of gate level. My intention is like structure level modeling. Okay, if you want to design a full adder, then you can take a two off adder and OR gate, instantiating in your full adder model, then you can design. This is a structure way of doing, okay, designing a model. See another example. So 2:1 max. So 3 inputs I0, I1 and one selection line. Based on the selection line, output may be either I0, I. output equal maybe I0 or I1. So this is a truth table. If selection line is 0, so output Y is now I1. So now output may be I1. Clear? So based on this selection line, that output may connected I0 or I1. So this is a Boolean equation for this 2:1 mux. If S is equal to 0, for example, 0 complement 1, 1 into I0 plus 0 into I1. So Y is equal to I0. If S is equal to 0, this expression Y is equal to I0. If S is equal to 1, 1 complement 0, this becomes 0, 1 into I1, Y is equal to I1. So based on the selection lines, whether Y is equal to I0 or Y equal to I1. So now this is the logic diagram for this given mux. Clear? I hope you know how to draw this logic diagram by using corner map. By simplifying that, you can write directly, or simply now see this is the simple logic diagram for 2:1 mux. Like that, here this AND gate, S0 I0, okay, S bar and I0 is AND gate. So here S bar means the NOT gate. So S bar into I0, this OR gate plus S0 into I1, this is another AND gate. So simply that way also we can write the logic diagram. So you need to write a Verilog code in gate level modeling for this 2:1 mux. Clear? So you know the logic diagram for 2:1 mux. By using this, you can directly write down. So now mux using gate level modeling. So module name mux 2:1, 2:1. So one output Y and the three inputs I0, I1 and selection line I0, I1 and S. Output equal to Y, and these are the input I0, I1 are the inputs. So I use some intermediate signals S bar, W1 and W2. I need to declare those signals, okay, as a wired type. So wired W1, W2, S bar. So first coming to this AND gate. So this AND gate has the two inputs. One is I0, another is the S bar. Clear? How do I get this S bar? So now by using this NAND gate, so if I provide input as S, then output is S bar. Now instantiate NAND gate, then output is S bar, the input is S. Okay. So now instantiate NOT gate, the output is S bar and the input is the S. It has only one output and one input like a buffer and NOT gate. Okay. Now here AND. So output is W1, one input is I0, another input is S bar. So for this AND gate, so now AND one output is the output is W2, one input is I1 and another output is S. So I1 and S. You know that NOT gate. So now we are using a OR gate here. So OR, the output is Y having two inputs W1 and W2. Like that, by instantiating these two AND gates and one NOT gate and one OR gate, then we'll describe the 2:1 mux using gate level modeling. I hope you understand, okay? Right? Now, designing a 4:1 multiplexer, clear, by using gate level modeling. So now having actual 4 inputs and 2 selection lines and 1 output. This is a truth table. If selection both are 0, 0, then output equal to I0. If selection line 0, 1, then output equal to I1. So 1, 0 output equal to I2. 1, 1 output equal to I3. Right? So now if you see the logic diagram for 4:1 mux, now this is a simple logic diagram. Clear? These are a selection line S0 and S1. So by using this NOT gate, we are getting S1 prime and S0 prime negation, like two more signals. By connecting these, okay, control signal to the AND gate and I0. Now simply can write, if for example, if S0 and S1 both are 0, 0, both are 0, 0 means, you know, this line 0 complement 1. So now connected 1 to this, and also S0 complement 1, okay, 0, okay, S0 is 0, 0 complement is 1. So these two signals are 1, 1. Now this AND gate, that output is depends upon this I0. Clear? So Y0 is equal to I0. So remaining all, in all cases, okay, if S1, S0, 0, 0, in the remaining these control signals, okay, becomes 0 for this all AND gates. Then Y1, Y2, Y3 becomes 0. Only Y0 should be based on this I0. Clear? So now this is a simple logical diagram for this 4:1 multiplexer. By this diagram, how do I write a Verilog code in gate level modeling? Now see, module name 4:1. So output and the remaining are the input I0, I1, I2, I3, selection 1 and selection 2. So you declare both, this is output, these are the inputs. So these I0, I1, I2, I3 and S0, S1 as the input signal, out as the output signal. So you need to declare some intermediate signals. Clear? So now this S1 negation, S0 negation, and this Y0, Y1, Y2, Y3 all are intermediate signals. These are the signals used inside the module, internal hardware architecture, right? Now these are the actual input, this is the output. These signals are intermediate signal. For our convenience we used, right? So now first not gate here. So now if provide S1, I need get S1 bar, okay? S1 negation. Another not gate I instantiate S0 as the input, S0 N as the output. This is the negation, right? So now 4 AND gates are there. So first AND gate, output is a Y0, another input is the I. So one input is I0. Next two inputs are S1 negation and S0 negation, like this. S1 negation and S0 negation. Same way this AND gate, output is Y1, okay. One input is I1, okay. Another input is, see here, S1 negation and S0. Directly I connect S0 and S1 negation. Clear? So similarly here, if you see, both are negation, S0 negation, S1 negation, you'll get here S1 negation, S0 here. So here S1 and S0 negation. Simply here S1 and S0. Y3 is output, I3 is another input. These are the control signals. Clear? Selection signals. So directly you can write by seeing this truth table itself, you can write this, okay, code. And here one output OR gate, okay. OR output is, okay, output signal, and 4 inputs Y0, Y1, Y2, Y3. So simply we can describe this hardware by instantiating these 4 AND gates, OR gates, and 2 NOT gates. This is the simplest way to write, okay, Verilog code, especially in gate level modeling. Okay, so this is the lowest abstraction level used in the Verilog. But if you want to design a complex circuit, we never prefer this gate level modeling. But you should understand how to write, okay, how to design a circuit in terms of gate. So at the post synthesis, we have netlist in terms of gate level only. In this video, we discuss a gate level modeling in Verilog with some suitable examples. I hope you understand how to write, okay, Verilog code in gate level modeling, okay, for various digital circuits. Thank you very much.